So welcome to the last session of this morning. We have our first speaker here, which is Wojciech, which is going to tell us about breaking cosmic degeneracies with non-standard observables.
Thank you very much. Good morning, everyone. It's a great pleasure to be here and have a chance to share some thoughts with you, for which I'm very grateful to the organizers. I think the purpose I have for this talk is that maybe not necessarily show you all the results, but maybe to convince you to some kind of a narrative argument I was trying to put forward in a different audiences than just the CosmoVerse for years. And I found this audience perfect to maybe make again this point and connect with you. Especially this audience with many experts with the biases and the degeneracies and tensions in cosmologies, and especially also in this CosmoVerse great cost action. So I will make more comments later what I'm actually meaning by here. But let's just go back to some standard things, and then I probably will make clear what I really mean. So of course, let's go back to standard model of cosmology. It's a great success, amazing success, even though it's a very simple model. Some people would say it's also very blunt because it contains a lot of chronological parameters. It's very successful. Let's remind ourselves that it's actually built of quite strong core assumptions. So it assumes there was a hot relativistic Big Bang. It assumes that the initial conditions for structure formations were Gaussian, adiabatic, probably produced by inflation, but inflation is just a hypothetical part of the standard model. It assumes global homogeneity and isotropy, which definitely is okay in the early universe. We see it's good confirmation in the CMB. At late times, it's still under scrutiny, at least maybe what scales we can talk about when we think about homogeneity and isotropy of the universe. The core assumption also goes back that the dominant component of the non-relativistic matter is the dark matter. It doesn't interact with electromagnetic forces, mostly via gravity only. We know the dark matter has been detected in CMB, at least with 40 sigma. Of course, you can dispute, but basically if you follow the simple physics of the photon plasma fluid and the compression rarefactions and compression peaks, so all these peaks, first to second and second to third ratio, really constrain that the dark matter, some form of the non-baryonic dark matter, this is what I mean by dark matter, has been detected by 40 sigma. Physical nature unknown, still under detection. Earth-based laboratories and our colleagues from the accelerators struggle to find any proof of, like really tangible proof of dark matter particle. And last but not least, GR, our beloved general relativity, is the theory of gravity on all scales which we take to build up the background model of cosmology. And GR has been tested tremendously on many scales and in regimes, but when it comes to scales, it's mostly solar system scales. Even if you think weak regime like planets, orbital motions, or strong regime like black hole mergers, it's still astrophysical scales at best. So we still don't have a separate, very stringent test of GR on intergalactic and cosmological scales. So the many tensions we observe in the modern cosmology, or hand for systematics and trying to get better understanding what we see there, might come from, exactly, unknown systematics, that's actually obvious, trivial, or from new physics, which will be something super exciting. And new physics can come in different forms, but maybe we also should remind ourselves that some of these core assumptions that we take for granted shouldn't be taken for granted. And what happens if you start twigging around these assumptions, what happens to the background model of cosmology? So in this talk, I will take, for example, the last assumptions. I will try to move away from GR a little bit, just to make my point. I'm not necessarily a great fan of moving away from GR, but we have some freedom there. And this is just to make my point, because I will be talking mostly about the growth rate of structures, not Hubble tensions, not weak lensing tensions, but I think some points I will make are very strongly connected, hopefully. All right, so GR is a beautiful, successful story of metric. That's just most general action, Einstein-Hilbert actions, but all these components are basically our metric of space, connected with the metric of space-time. And of course, if you know, the Lovelock theorem tells us that with these actions, we get at most second order of equation of motion, so this is like most general actions. But you can generalize terms in those actions, and you can play around, because you have some freedom here, at least on the model building space. So I won't gonna go into details how you can modify the gravity at GR. Actually, we don't no longer use modified gravity term. Now people tend to and like to use extended gravity theories term, in a sense that it's more capturing the essence, because we're not modifying GR. GR is still there, we're just extending, adding some extra degrees of freedom in the action. So it's like a phenomenological level. So we already have dark energy that is quite phenomenological and dark matter purely phenomenological. Why not play around with that? And of course, there's so many possibilities. I'm not the model builder, but if you love Lagrangians, you can go to the Einstein-Hilbert actions and build models and try to see which are of the stables, which are free of Gauss, and then maybe later see which of these models extensions actually make sense with the late time, early time cosmology, allows for the structure formation, so on and so forth. But it's basically many models survive this kind of a play around, and there's a huge landscape. I would try to tell that, of course, there's no point maybe taking one model at a time and build full cosmology and convince someone to send a probe there, or space or probe or telescope. Let's try to put as many theories as possible under one umbrella and try to see what you can do, if there's any room maybe to going beyond or extend gravity. Okay, dragons be there, Pandora box, there's plenty of options. But basically, extend the theory of gravity or / dark energy and testing GR intergalactic scales. I would say put this everything into one category. I think it's one of the bold and great tasks of 21st century extragalactic astronomy. You have plenty of different surveys from in the past 20 years and is going into the future that were built and designed in mind with actually accomplishing this goals, basically testing the growth rate of structures on intergalactic scales precisely, testing expansion history, testing all these things that we have in the standard model. We can build different kind of probes. This is just a slide to show you that different physics and different kind of observables probe different scales when it comes to dark energy or GR or modified gravity. And I will be talking about some of them. But actually, yeah, so some of the logos of the main great surveys that are actually already producing the data or will very soon start producing the data. And by the way, maybe this is not really surprising that we find so many inconsistencies, interesting things. So we find tensions, few sigma or even many sigma level discrepancy. Already 20 years ago, I'm not that old, 20 years ago, I wasn't even, I was a very young PhD student. No, I think master student. But already back then, I think people were expecting that with all these new surveys, with all the volume increase of the data, we're going to reach soon enough regime times when systematics errors will become dominant over the basically random errors, right? So basically, we really nailed down. We have so much data that random errors are completely subdominant, and now we worry about systematics. And this systematics might be new physics or might be some instrument base. I would try to convince you that there's also systematics related to the model-based assumptions, including the cosmological model. So let's say, okay, we have this extended theory of gravity. Pick your favorite. I'm going to be showing some of them. Let's not pay too much attention on what particular model I mean. But let's say we have some freedom. This modified gravity theories, the term stacks in my brain. Extended theories of gravity are built in a smart way, so they need to pass all the solar system and strong field regime tests, so they involve something we call screening mechanism. The physics is not very important, although it makes it very interesting. What's important is that it's quite too hard to make high-level prediction for these theories, because modeling non-linear regimes is already hard for lambda CDM, and for these theories even harder. But let's say we want to stake to some reasonable scales. How would you go about? Well, you run a simulation, which is the best tool we have to study structure formation into the nonlinear regime, and you just have some prediction about the clustering. So how to quantify, of course, take power spectrum. In linear theory, you can define the growth of power spectrum by solving the linear perturbation theory. And then, of course, immediately fundamental parameter pops out, growth rate, linear growth rate of structures. So basically, it's a linear derivative of the growing mode of this equation here. And if you play around with the structure formation, if you play around with the GR and have extra degrees of freedom, some of these theories will tell you that on intergalactic scales, there can be some extra force that would modify this scenario. So again, I'm not going into any details about is it really reasonable or not, but there can be some freedom. So by measuring this growth rate quite precisely and comparing with the prediction of GR, maybe we can reject some of these models. And this is what we do also with, assuming what lambda CDM predicts for H naught, or what lambda CDM predicts for the sigma 8 omega matter and other parameters that we measure, for example, in weak lensing. So This particular example I will try to walk you through is about the growth rate of structures. So indeed, if you go to this modified gravity theories and plot the power spectrum, in linear theory, you see this is the ratio to the GR. At the bottom, you will see that there's some prediction of enhancement. Some will predict enhancement on all scales, but okay, maybe you can say they'll falsify, but if they predict just few % enhancement, then they hide into the unknown systematics. Some model predicts actually scale-dependent enhancement of the growth rate. This is actually f of r. But all of them basically have some kind of a prediction that they, even at linear theory level, predict that some of this growth rate should be different. So how would you go about measuring this? Well, you see the power spectrum. Okay, let's go and try to measure this in this regime. Obviously, you immediately arrive at the big problem that you know that on top of the gravity-only interactions, we have baryons in our universe that feel pressure, that do complicated stuff like form stars, form galaxies. Some of the stars explode, inject energy back again, and the gas is heated and cools down. It's all this complicated baryonic physics that it's complicated but produce these beautiful shiny things, which we call galaxies, which we observe, but also makes it very hard to use this prediction of the total matter power spectrum, which, for example, you could take immediately to lensing measurement. Why? Because this is actually quite old example from Ewald Puchwein paper, but we have also some more hadronic simulation of this extended theories of gravity. Enhancement of this power spectrum of the modified gravity, which is just, so dark matter only, gravity only simulation will be the thick line. If you convolve this with baryonic physics, which from simulation we don't know from first principles, all this how strong is supernova feedback have to be tweaked around to get something reasonable. How strong is AGN feedback has to be put into simulation and tweak around. So basically these parameters are called subgrid physics and we constrain them by observations. But you have freedom to play with them. So if you make the AGN feedback stronger, you see there's a degeneracy. You can suppress the power spectrum on small scales. So using the total matter power spectrum for this particular test is a bad idea if you don't have a full understanding of baryons and how we don't even know how baryons should be modeled well in LCDM, not to even mention going beyond GR. So what you do, of course, forget about the total matter power spectrum, we can use the galaxy power spectrum. So this is, of course, big industry. It's called redshift space distortion observations. So here's an example. You have a real space position in simulation. You can make it redshift space when the observer is here. So you see fingers of God, all these effects are there. You can measure 2D galaxy correlation function, and you have some amplitudes. There's actually 3 different galaxy mock catalogs, let's say. And actually, I have some modified gravity, extended gravity theories here. So you see they're all near each other. Of course, the devil is in the details. So you can build this into a machine. And what you do next, of course, well, since you predict linear theory power spectrum, but you observe the redshift space, you need to have a transformation from real space to redshift space and all the way around. So actually to go from measurement back to the theory to the parameters that are working on the configuration space. This is all well known, this is just industrial standard. So basically this is one of the most general power spectrum, redshift space power spectrum models. So you have this D, which is the velocity damping term, what happens inside visualized structures on the line of sight. And you have a general model of the power spectrum on large scales, which actually involve this many different terms like growth rate, bias, and velocity power spectra, velocity density cross power spectra, and density power spectra. But you can build a model like that, and of course this has been done. And then you produce beautiful plots like this. These are usually money plots for the spectroscopic galaxy surveys that measure growth rate. You have a redshift, and you have a F sigma 8. And sigma 8, this is of course parameter that has been treated here as a nuisance parameter. It's not to be measured, it's just to be marginalized. And then usually you have some data points, and then some predictions, and even some extended gravity model lines that are predicted to be better or worse matching the data. But the problem is that if you go back to this picture, you understand that all these models, this is actually velocity dispersion in the line of sight, this is the growth rate, this is the different power spectra and bias, they can behave differently in different theories of gravity. And what industry usually does takes the LCDM, because it's not surprising because we have most of the manpower in the LCDM working pipelines. It's very hard to build, like in a small team, such a big machine just for one of the particular extended gravity models, for example. But bear in mind that these things like bias, velocities, dispersion can be different in modified gravity. So what happens actually here is that position of these points are model dependent. If you change your model of the redshift space distortion, and by changing a model I mean background model of the universe, change the theory of gravity, for example, and change the different growth rate of structure, positions of these points will move. So this is not like direct measurement, of course, it's derived measurement.
Sorry, is that also when you change the metric?
Metric?
Yes.
Which metric?
The new metric in your theory. Like
Say.
you will have the shift if you like you construct another metric, you will also think the GMU.
Yes. So these are, well, I'm talking about scalar tensor theories, basically. So these are just, have extra degrees of freedom that couples to metric and to the matter fields in a special way. So the Einstein equations are still valid, basically, but you just add the...
Then you don't change metric at all, so it's minus 1, 1, 1.
Yes. Yes. Well, we don't go that far. Yeah, we don't change metrics. You still have a theory of metrics. So I'm running out of time, so try to actually show you what started happening. So a couple of years ago with my former postdoc, Jorge Garcia Farieta, we said, okay, let's try to do this in a more, well, I would say more honest way, but less assumptionist way. And we took simulations of these theories, and we tried to extract from different mock galaxy catalogs the growth rate of structure, but actually not bare growth rate of structure, but this beta parameter. It's called actually distortion parameter. In 90s and 80s, this is what were people modeling and actually measuring because the galaxy bias weren't that well modeled because there was some simulation. So it takes the growth rate divided by the galaxy bias. Normally, you just approximate galaxy bias from your survey saying, I know sigma 8 from the CMB, Planck, whatever, and I marginalize it and I get some number, so that's why I measure F sigma 8. But if you do it in this way, you will see that there's a bunch of points here that are all close to each other, and the line is prediction from another theory. You see even lambda CDM sometimes is away from the line, right? So this means that, you know, first of all, points become much closer to each other if you extract exactly what is being affecting these redshift space distortions, not assuming model. And second of all, even the lambda CDM, which is our standard model, might not perfectly lie there. So we move further this exercise by actually going back to the linear perturbation theory and build templates. People use templates for redshift space distortions. For one of the particular modified gravity model, we invest, okay, we know there's many of these theories, let's build the template for one and compare what would happen if we have these pipelines, like in Euclid, for example, for lambda CDM and modified gravity. And what we did, and this plot is summarizing this, we inject some growth rate here, which is like true growth rate from simulations. And now, if you have a pipeline that is not agnostic about modified gravity, but includes this particular modified gravity parameters, you get, this is a 2 sigma error bars. You get measurements right on spot. But if you naively apply your GR, lambda CDM pipelines, redshift space distortions, on the modified gravity simulations, you get bias, nearly 2 sigma away bias measurement of the growth rate. So this actually shows you that you have to be very careful with interpreting what you have measured. Of course, if the universe is GR and you're using GR pipeline, you have a self-consistency check. But if the universe has different physics and you're using wrong pipeline, you might arrive at the biased measurement. So it doesn't mean that you actually falsify these extra theories. So what you can do about this? Maybe with the growth rate, you can try a different approach. For example, we know that this redshift space distortions arise due to the peculiar velocity motions on the line of sight that are interpreted as a distance. So what if we could take the direct measurements of velocities? This can be done if you have a redshift-independent distance indicators. And there's been a great field built mostly by Brand Talley, effort of one single man that single-handedly put many of thousands of galaxies into the database. So these are the survey. This is a survey when we, from different methods, supernovae, Talley-Fisher, fundamental plane for optical galaxies, and so on and so forth, build kind of a peculiar velocity data for nearby galaxies. And you can use basically the line of sight, basically velocity, to try to measure these velocities directly. And actually, you can go and see what would happen in that case if you would have this kind of a power. So this is what I'm showing is actually pairwise infrared velocity. So you group galaxies in pairs and measure basically by observables how what is the component connecting the galaxies together. So galaxies have a tendency to have this negative velocity at small scales because gravity works. So galaxies tend to get towards each other. On large scales, this velocity average out to 0. So this is a result from a recent paper with Mariana Bravo-Haber, who are actually going to give a very nice talk tomorrow, which I advertise, about different model and different thing, but also very interesting. And you see that different modified gravity models give you different prediction of the spiral velocities, which is kind of something that doesn't involve, if you could measure the spiral velocities without assuming the gravity model, you could go directly to these predictions without model-dependent assumptions and make the measurements. So we've been trying to do this for some time now, and unfortunately, there's one additional complication. So even though these velocities offer you, in principle, model-independent, model-unbiased way to measure growth rate or test the structure or formation scenario, they're only available to the limited distance. They are very locally because the error grows with the basically distance modulus, so the errors on the distances of the velocities explode. So maybe up to 100 megaparsec, maybe 150, you can trust the data, then data is dominated by errors. But if you play this game and you understand that the velocity field has a much stronger correlation than the density field, you can get something like that. So this is what this is going to be my last slide, and let's jump to conclusions. We try to find for a local group-like observer in a big simulation. So we ask, should there be a Virgo-like cluster nearby? Or should we sit on a halo? Should we sit on a halo that moves with respect to CMB with some velocities? And it turns around that most of these questions actually have impact of what kind of a thing you're going to extract from your survey, because velocities really fill these nearby peaks like Virgo cluster or Shapley concentration or Coma cluster. If we ignore these phases, that are just random phases around us, you're going to get a completely biased measurement. So this is, for example, random, which we call Copernican observer, would measure if we could go over the whole universe. But this is what actually biased local observer measure. And the problem is it's not easy to account for this observer bias now. It's not theoretical bias, but observer bias. But there's a way, hopefully. My point is that if you could make this measurement, you could compare this growth rate of structures with the redshift space distortions spectroscopic survey parameter and see if you get the same thing. If you don't get the same thing, maybe A, there's a new physics, or B, there is a different universe that you're applying your pipeline for, or there's another systematic. So I'm sorry for running out of time. I had one more piece, but of course I don't have time for this. Forget about it, don't worry. And this is my take-home messages. So it's crucial to test GR, and also all of these core assumptions of the standard model on cosmological integratic scales. Clean tests for these assumptions, and in particular of GR, are hard to achieve because there are many degeneracies leading to systematic effects. So we might outlook for difficult alternative methods like velocities, which I just only had time to mention, which are hard, but I think they are very worthy because the self-consistency checks teaches us a lot about other data sets. Thank you very much. I'm looking forward to your questions.
Okay, thank you. Questions, comments?
I see in your figure you use N1 and N5. So when you assume N equals 1, which FR will you use?
Okay, as I said, I try to ask you not to pay attention because these models have their own particular parameter space, of course. And this, in particular, in the case I was showing as a case study, letter N corresponds to something we call NDGP theories with Weinstein screening. So N1 is just means it's 1 gigaparsec is the crossing over scale to the 5th dimensional gravity, because this theory has this one main parameter. Effectively, what it means that it has around 8% higher growth rate than lambda CDM. F5 was when you spotted F of R theory, with this 5 corresponding to 10 to minus 5, the parameter of the scalar field today, which also increase the growth rate, but on linear scales converge to GR. So different kind of theories. So of course, they have all the parameter space, but at least what I'm trying to say, they predict some differences. And if you can control about systematics and model-dependent biases, maybe you can invalidate these theories. That would be my hope, because I like GR.
I remember current cosmological constraints on FR0 is about 10 to minus 5. So if you're using the the velocity.
Yeah.
So what's the
So that's the difficult question. I would say with f of r, which is a very peculiar theory, in a sense, it's not necessarily the fact that the weaker the modification to gr is, the easier it is to model, because there's a f6, 10 to minus 6 variant, which is still below constraints, is allowed, but it behaves so non-linearly on the galaxy levels that it's actually harder to model than f5, for example. So you would have to have dedicated simulation. It's basically, as you see here, f6, okay, sorry, is quite close to lambda CDM, but still, you know, there's still some room that, given the error bars, the signal could be significant. Of course, it's closer. It's harder to use the velocities just to constrain model that is so luminal.
Hi. So you showed the plot that was, I think, from Ben Rose's paper.
Yeah. Well, this one.
This one, yeah. So one thing I noticed is that the size of the error bars are different. Is this something you expect, or do you understand why?
In a sense, yes, because these are 2 sigma error bars, and if you apply, let's say, wrong template, it has a much more wiggle room in the velocity dispersion damping term, and then if you do the proper matching, the chi-square distribution becomes wider, so it predicts a bigger error. While the proper pipeline, let's say modified gravity, because it has a less freedom in this velocity dispersion terms, gives a tighter chi-square distribution. And if you would have this all the way around, basically, you would get, so if I would say I apply modified gravity template to the GR universe, you get the same error bars as GR, because then this extra parameter that is unconstrained in GR doesn't widen the error.
Is this something that can be used as well to see?
Yes, yeah. Well, the velocity dispersion is a interesting parameter. We try with Jorge quite hard to see if we can extract this parameter just as it is from the spectroscopic survey. But the problem is that, well, all the models we have are quite simplistic and unphysical, and for the distribution of the Paris velocities, well, not plus, but if you have good models, it's hard to apply. So in principle, the answer is yes. It actually will be powerful. Something I haven't shown, that the velocity dispersion is much strongly affected by modified gravity than the mean inflow, which is just the first moment. But it's harder to use it as a measurement parameter. But it's possible in principle.
I don't think we have time for more questions, but let's thank the speaker again.
Thank you.